We're going to get into a little bit more detail now about capacitors. We're going to talk about some capacitors that are not just parallel plates. We're going to talk about cylindrical capacitors. We're going to talk about the energy stored in capacitors. And we're going to talk about how we can use dielectrics to make better capacitors. So let's look at calculating the capacitance of something that is not just parallel plates. So this is a very long cylindrical capacitor. So we have an inner cylinder that has positive charge plus Q and charge density plus lambda. And we have an outer cylinder out here with charge that's negative Q. And so the electric field between them is just going to be due to this long cylinder, and we calculated in class that the electric field due to a long line of charge is 2k lambda over r. And here, the inner radius is A and the outer radius is B. Now to calculate the capacitance, we need Q and V. So to find V, we're going to have to do an integral because the electric field is not constant here. So we're going to use this equation here for V. So V is minus the integral of the electric field dotted into ds, the electric field here. And we're going from, and the way we do it is we do it from the negative to the positive. Okay, so let's plug in for the electric field. It is 2k lambda over r times the ds, which in this case is the radius, it's dr, and the angle between them. Since we're integrating inwards and the electric field points outwards, there's an extra -1 sign there because it's cosine of 180. The two minus signs cancel out. Let's pull out the constants. 2k lambda. It's the integral from the outer to the inner, so from B to A of dr over r. And if you look at that, that's just the integral of 1 over r is a natural logarithm. We plug in the endpoints and we simplify. We end up that the voltage is 2k lambda natural logarithm of B over A. So we're basically almost all the way there. So all we need to do now is calculate the capacitance, right? So the capacitance is Q over V. So Q over 2k lambda ln of B over A. Okay, and now for lambda, I'm going to use that lambda is equal to charge divided by length. So this becomes Q over 2k Q over L ln of B over A. And that simplifies down. You see the Q's cancel out there. And we get and if I plug in for K, I'm also going to use that K is 1 over 4 pi epsilon naught. I get that we end up with 2 pi epsilon naught L over the natural logarithm of B over A. So that would be the capacitance for concentric cylinders, which is kind of cool. And this is the answer you get when you do that derivation. You could do something similar for spherical capacitors. So if they're spheres instead of cylinders, right? The electric field for between the spheres is going to be kq over r squared instead of k lambda over r. And you would do a similar calculation, and you would get this: that c is 4 pi epsilon naught AB over B minus A. Next, I'd like to look at the energy that is stored in a capacitor. So if I attach a capacitor here to a battery, the battery charges one side of the capacitor positively and the other side negatively. One way to think about it is it takes positive charges from one side and moves it to the other side and charges up this capacitor. And this little stairway represents that it's sort of spending energy to raise it to a higher energy level to get it over here. So this escalator does work to move the charge dq from the negative plate to the positive plate. So it's change in potential energy depending on the amount of voltage. So it does a small amount of potential energy change for a small amount of charge depending on the change in voltage. All right? And if I replace delta V with Q over C, I have that du is equal to Q over C dq. So if I integrate this, I get the potential energy stored in the capacitor. So I integrate this Q dq between an uncharged capacitor and a fully charged capacitor, and I end up with the energy stored in a capacitor is Q squared over 2C. So the amount of energy that is stored by the capacitor depends on how much charge is on it. Or if I use that Q is equal to CV, I can rewrite this equation here as, if I plug in that Q is equal to C times V, I end up with 1/2 CV squared. It's the same way of saying the same equation. That tells us how much energy is stored in the battery. Or, again, if I wanted to, I could say, I could replace the C with C is equal to Q over V, and I could rewrite this equation in another form, which is 1/2 QV. So we have the potential energy stored, and we can write it 3 different ways, and it gives us the same thing. It's the energy stored in the capacitor, and I can use that I can discharge that energy and use it to do something else. So just as a sort of, so these are the 3 versions of the same equation. All I did is you can use Q equals CV to rewrite the expressions, but that's the energy stored in them in all 3 cases. So let's just do a simple example here. We have a 2 microfarad capacitor that's attached to a 300 volt battery. Happens all the time. Why not? So let's draw a picture and then figure out how much energy is stored in that capacitor. So here's my 300 volt battery, and I attach it to a 2 microfarad capacitor. Right, so this is going to become positively charged on one side and negatively charged on the other side. So I can calculate the energy stored. In this case, it's just going to be, in this capacitor, it's going to be 1/2 CV squared. So 1/2 times C, which is 2 times 10 to the minus 6 farad, right? It said 2 microfarad, times 300 volts squared. That all works out to, the units work out to joules. So we end up with 9.00 times 10 to the minus 2 joules. So there are 0.0900 joules of energy stored in this capacitor. If I want to do another example here, just to make it a little more fun, let's say I have a 2 microfarad capacitor, and it's attached to a 4 microfarad and a 2 microfarad capacitor and a 4 microfarad capacitor are both attached in parallel with a 300 volt battery. So here's that 300 volt battery again, and we're attached to 2 capacitors in parallel, so one after the other, like this. So this one here is 2 microfarad, and this one here is 4 microfarad. And the voltage across each of them is going to be 300 volts because they are in parallel across this battery. So remember, the voltage from here to here is 300 volts, which means that the voltage from here to here is also 300 volts, which means that the voltage from here to here is also 300 volts. So the voltage across each of them is 300 volts. And so now I can find the energy stored in each case. So for this case here, I can get the total energy stored in capacitor 1. It's going to be 1/2 CV squared, and I plug in all the numbers, I get 0.090 joules. When I do it for this one, same thing, right? 1/2 CV squared, that is 0.18 joules. So the total energy between both of them, if I add them together, right, is going to be 0.27 joules. That's how much energy is stored between those 2 batteries together. So another way to think about how the energy is stored in these capacitors is by looking at the energy density. So imagine we have a certain amount of we have a capacitor with an area A and a distance D. We can consider the energy stored in this capacitor as being stored in the electric field created between these. And so the energy stored would be UC. And how much energy is stored? Well, let's divide it by the volume in which it's stored, if it's stored inside the electric field here. So you take that and you take the 1/2 CV squared and divide it by AD, and by playing around with the equations you can show that the energy is the energy density is directly proportional to the electric field squared. In other words, it's how much energy is stored between cubic meter of for every cubic meter of electric field. Next I'd like to talk about dielectrics. So dielectrics are anything that you place between the 2 plates of a capacitor that is not a conductor, because if it's a conductor, the capacitor can discharge, right? The charge will just go from one plate to the other. So a dielectric is something that you place between these two plates, and we'll see what effect it has on it. So when the capacitor is fully charged, right, it has with a voltage delta V naught. So the naught is going to represent when we're doing things without a dielectric. It has charge on it plus and minus Q naught. Okay, so when you charge it with a voltage, it's plus or minus V naught, and the plates will be plus or minus Q naught. Now when I place a dielectric in there, it's an insulator because the charge doesn't go across it, but something happens. The charge on the place doesn't change, it's still Q naught. Alright, the new Q doesn't change. If it's not attached to a battery, it's still Q naught. However, we see that the voltage goes down. When I put this dielectric in there, there's the same charge, but the voltage went down, which means that the capacitance went up. So we increased the capacitance by placing this dielectric between these two plates. Now how did that work? Well, one way to think about it is, here's an insulating material. Let's say it's a dielectric, and we put it inside the plates. It's inside an electric field, right? And that electric field is going to warp the molecules inside there. Remember, the electrons aren't free to move around, but you could warp the molecules and push the positive side to one end, the negative side to the other. So the whole thing is still neutral, but it tends to separate the positive and negative charges a little bit. And that separation of charge makes one side slightly positive and one side slightly negative. And that creates an electric field that cancels out some of the initial electric field. So here's the initial electric field. Now the new electric field depends on how much is canceled out by that polarization that happens. And so now we have this electric field that cancels some of it out. So the new electric field is going to be lower than the original electric field, which means the new voltage will be lower than the original voltage. So how much the electric field is reduced depends on the material that you put in there. And we call, and different materials will reduce the electric field by different amounts. And we call that relationship the dielectric constant. So any material that you place in there that reduces the electric field is going to reduce it by a certain amount. That's the original electric field divided by the new electric field. So this is a property of the given material. It's like density or specific heat, right? It's a property of that material. Vacuum has, and that's the Greek letter kappa, it has a dielectric constant of 1. So if I have a capacitor that's Q over Vc, right, I think about, well, if that Vc was due to a capacitor, that means there was an original V divided by the dielectric constant. And when you factor out that that dielectric constant, you get that the new capacitance is equal to the old capacitance times kappa. So kappa is always going to be 1 or larger, because this is going to be equal to this when it's a vacuum. Okay, so the capacitance gets increased when you place a dielectric in there. And production of capacitor, it's practical, right? You want some way to separate. If we have two sheets of metal that we want to use to make a capacitor, if you want a lot of area, you roll it up and you put something in between them and keep them separate. And if that dielectric also increases the amount of, if it also increases the capacitance, that's even better. And the breakdown of electric field of air, as you very well know, is about 3 times 10 to the 8 volts per meter, right? That's a certain point at which, if there's too much voltage difference across here, the current will just jump through the paper. So a material's maximum sustainable electric field is dielectric strength. So its dielectric strength is kind of related to this breakdown. For air, it's 3 times 10 to the 6. For paper, it's going to be something different. Here's some examples, right? For dielectric constant is how much it reduces. It's a measure of how much it reduces the electric field. And it's related to its dielectric strength a little bit. So air slightly does not do a very good job, does not change things much. It's basically the same as vacuum. The dielectric strength in megavolts per meter for air is about 3. If I were to put Teflon between the two sheets, its dielectric constant is 2, so it doubles the capacitance. If I put paper, it almost quadruples the capacitance. If I put pure water, and that's pure water completely deionized and nothing in there, then it's not a conductor, and then it would be 80 times. But that's a hard thing to use as a dielectric. Here's like strontium titanate as the king of the dielectric. If I put strontium titanate between my plates, it increases the dielectric it increases the capacitance by a factor of 300. So just a simple example. Let's say I have a capacitor here, and it is attached to a battery, like this. That's a very big capacitor. Let's say this capacitor here is 10 microfarad, and it is attached, let's call it C0 because I haven't inserted a dielectric yet, and it's attached to a battery with a voltage of, I don't know, 72 volts. Okay, so this is, we can even calculate what the initial charge is on this. What is the charge on this? Well, in this case, Q is equal, I can use Q is equal to CV. So Q, the amount of charge would be 720 microcoulombs. And the voltage across this, because it's still attached to the battery, the voltage across this is going to be 72 volts. Right? So that's charging up the battery. We put a voltage across it, we put some charge on it. So now I'm going to remove the battery, just for fun. So if I remove the battery, then I just have this. I have my capacitor here, and it still has V0 of 72 volts. It still has C0 of 10 microfarads, and it still has the charge here of 720 microcoulombs. So it's still charged up like it was by the battery. Okay? So now what we're going to do is we're going to add a dielectric. We're going to add a dielectric, and it's going to have a dielectric constant of, let's say, dielectric constant of 4. So if I add a dielectric to this thing, so now this is still positively charged, and now this is negatively charged, and so I've added my dielectric. Okay, so it's not attached to a battery, so the charge has nowhere to go. So the charge stays the same. It has to be the same charge. It had nowhere to go, so it's still 720 microcoulombs. So that's the same as the charge before because there was nowhere for it to go. All right. The new capacitance is equal to the old capacitance. Capacitance is equal to kappa times the old capacitance, right? So it'll be 4 times 10, so it'll be 40 microfarad, which means we can find the voltage for this thing. Just use V is equal to Q over C. So the voltage for this thing will be the charge divided by the capacitance, right? So it'll be 720 divided by 40. So 720 divided by 40 is going to be 18 volts. Okay, so we charged a capacitor up to 720 microcoulombs, and we put in this dielectric, and it increased the capacitance to 40. And since the charge didn't change, the voltage had to change to match it. We could have done it differently, right? We could have left it attached to the battery. If instead, so if I had done a different path, taken a different path in life, instead of doing it that way, what if I leave battery attached, I leave the battery, and I add the dielectric. I add the same dielectric with kappa equals 4. So let's think about that. So here it's still attached to the battery. That means because it's still attached to the battery, that means that the voltage stays the same. Because in this case, it's still attached to this voltage of, what is it, 72 volts, right? 72 volts. That means this is still 72 volts. It's attached to the battery. So the charge will have changed. And I've added the dielectric. So now the capacitance is now K times C0, so it's 40 microfarad. So the amount of charge will change because the voltage has to stay constant. So Q is going to be equal to CV, right? So it'll be, so Q will be C times V. So it'll be 40 times 72, which is 0.2880 microcoulomb. So when you remove the battery and you have this charge here, if I add the dielectric, the charge stays the same and the voltage goes down. But if I leave it attached to the battery maintains the voltage by changing the charge when I add the dielectric, and the voltage and the charge will go down. So let's compare that to the animation. So here we have a battery and a dielectric off on the side here. So if I turn on the battery, the plates get charged, positively and negatively charged. Now, if I were to disconnect the battery, right, the charge stays there. So now the charge has nowhere to go. So the amount of charge here, I'm going to turn on plate charge. So the amount of plate charge here is given, and the capacitance here is some certain amount here, 0.89 times 10 to the minus 13. When I place this inside, the capacitance goes up, the charge doesn't change, but the voltage goes down. So let me put this here and measure the voltage from here to here again. So if I measure the voltage from here to here, it's 0.3. When it was out, it was 1.5. And I put this in here, the voltage went down to 0.3. And you notice here it's showing how there's like a little charge distribution in there that's canceling out some of the electric field. And if I left it connected to the battery, when I place this in, the voltage stays the same, but the amount of charge increases. Okay, so you get the opposite effect.